Okay, so you've probably never even heard of it, but did you know there's a master controller inside your brain? It's working behind the scenes right now, fine-tuning your mood, your memory, even how hungry you feel. We're talking about the endocannabinoid system, or ECS for short. And believe me, understanding this system, well, it unlocks some absolutely incredible secrets about how our brains stay in balance. But right away, we run into this huge puzzle. The components of this system, they're not just in one spot. They are everywhere in the brain. So how on earth can it send a super specific message to one tiny little spot without, accidentally shouting at the entire neighborhood? How does it get that pinpoint precision when its tools are spread all over the place? This very question has fascinated scientists for years. Neurobiologist Dr. Lutz even calls the system's specificity amazing, and for good reason. It turns out the solution lies in two brilliant secrets of brain design, and we're about to uncover both of them. All right, so to crack this puzzle, first we need to meet the key players. Think of the ECS as a highly sophisticated communication network that's running inside your head 24/7. This network really has two main parts. First up, you've got the messengers. These are endocannabinoids, which are basically cannabis-like molecules our own body produces. The two big ones are anandamide and a molecule called 2-AG. Then you have the receivers. These are receptors, kind of like docking stations that the messengers bind to. And in the brain, the one you really need to know is the CB1 receptor. So, how does this widespread system get so focused? Well, the first secret is a classic: location, location, location. It's not just that the receptors are there, it's where they're placed with microscopic precision. And you can just see how widespread these receptors are. I mean, they're not just on the main communication cells, the neurons, but also on all these support cells like astrocytes and microglia. This just makes the mystery even deeper, right? If the receivers are everywhere, how can the message possibly be precise? But here's the solution. If we zoom way in on a single connection between neurons, we see that while the receptors are on many cells, they are clustered in one critical spot, the presynaptic terminal. Just think of this as the speaker's microphone. It's the part of the neuron that sends the signal out. So here's the crucial point. This strategic placement turns them into gatekeepers. By sitting right on that sending terminal, they can directly control the flow of information. They can essentially tell the neuron to release more, or, more often, less of its signal. It's like having a precision volume knob right at the source. But location is only half the story. The second secret to the ECS's precision is its incredible timing. You see, unlike other signaling molecules that are stored up and then released, endocannabinoids are part of an on-demand system. And this is where it gets really clever, and honestly, a bit counterintuitive. Most communication in the brain is a one-way street, right? From a sending neuron to a receiving one. But the ECS, it works backwards. So here's how this backwards system works. Picture this. A neuron receives a really strong signal. In response, it instantly, cooks up these endocannabinoid messengers. But, and this is the cool part, instead of passing the message forward, it sends them backward, right across the gap to the very neuron that just sent the signal. They latch onto those gatekeeper receptors we talked about and basically say, hey, got the message loud and clear. You can quiet down for a second. It's a perfect real-time feedback loop. This backward message has a name. It's called retrograde signaling, and this is the second secret to its precision. The signal is only created exactly when and where it's needed. It only travels a microscopic distance, and then poof, it vanishes. No widespread noise, just a precise local whisper. So we've got this incredible system of precision control, but why? Why does the brain even need such a sophisticated feedback mechanism? What's the ultimate goal here? And what happens when that fine-tuning goes wrong? Well, the ultimate goal of the ECS is to maintain what's known as homeostasis. The easiest way to think about it is as the body's perfect internal balance, its physiological sweet spot. The ECS is constantly working in the background to keep all of us in this optimal state. Take a look at this graph. That green peak, that's homeostasis, the healthy, balanced sweet spot we all want to be in. But chronic stress or other issues can push the system off that peak. It can actually get stuck in a new stressed out normal, and that state is called allostasis. It's almost like the body's thermostat got permanently set way too high. And this shift, It's not just some abstract concept, it has profound consequences for our health. A dysregulated ECS is now being linked to a whole range of neuropsychiatric disorders, everything from depression and PTSD to anxiety and addiction. So, yeah, maintaining that balance is absolutely critical for our brain health.
Okay, so this understanding opens up some really fascinating therapeutic possibilities. If we know how the system gets out of tune, can we find ways to gently guide it back?
The new goal for researchers isn't to just hit the ECS with a pharmacological sledgehammer, turning it all the way on or all the way off. No. The real art is in developing ways to gently nudge it back towards that homeostatic sweet spot. And this has led to some incredibly sophisticated strategies. Instead of just forcing the system on or off, scientists can now use tools with way more finesse. They can use things like enzyme inhibitors to just gently boost the levels of our own natural endocannabinoids. Or, and this is really cool, they can use something called allosteric modulators. Now, don't think of these as an on-off switch. Think of them more like a dimmer, right? They allow for these super subtle adjustments. The goal here is to restore the system's natural rhythm, not to completely hijack it. So let's just step back for a second. We have this master regulatory system literally built into our biology, one that uses the secrets of precise location and on-demand timing to keep our brains in perfect balance. This one system influences everything from how we feel to how we remember. So the final question is a big one. If this system is truly the key to our mental well-being, what could unlocking its full potential really mean for the future of brain health?